Today we're going to learn the principle behind the assignment of oxidation numbers within a molecule. The oxidation number assignment is due to the electronegativity of an atom within a molecule. The most electronegative atom gets all the shared electrons. Each atom gets all unshared electrons. So basically, what we're saying here is that where you want to determine where the electrons would reside if all the bonds were non-covalent. And then we can use this formula to determine the oxidation number, where oxidation number is equal to the number of valence electrons that that element would normally have minus the sum of the unshared electrons and the number of shared electrons. And then I'll give you your oxidation number. So we're going to work through a couple examples to highlight how this would work. So for fluoric acid, we have HF here. And so I'm going to start off by drawing the Lewis dot structure for fluoric acid. So we're going to have H, and we'll draw on our F here. Draw a bond between them. And then for the fluorine, we have 7 electrons. From the hydrogen, we have 1 electron for a total of 8 electrons. And so now I'm going to just count them like we've been doing in the past. 1, 2, 3, 4, 5, 6. We have our 2 from the bond for a total of 8 electrons. So we have used up all of our electrons. So now we want to go ahead and determine what this is for, let's say, the fluorine to begin with. So we want to look at fluorine, which is over here in the upper right hand corner. And for fluorine, it's the most electronegative element. So it's going to be more electronegative than hydrogen. So when we're determining its oxidation number, the oxidation number is going to be equal to the number of valence electrons. So since it is over here, we're going to count 1, 2, 3, 4, 5, 6, 7. So it normally has 7 valence electrons. Then we're going to subtract out the number of shared electrons, or sorry, number of unshared electrons. So in this case we have 6 dots, and the number of shared electrons. Now in this case, since fluorine is the most electronegative of the two, it's going to get all of these shared electrons. And so in this case, we're going to have 2 of those shared electrons are going to reside with the fluorine. All right, so now we can do 7 minus 6 plus 2, or 7 minus 8, and we end up with a negative 1. If we do the same thing for hydrogen, look at our periodic table. Hydrogen's in the upper left. We can count that it has 1 valence electron. So we're going to put down 1. Then we're going to subtract out all the dots that it has, which in this case is 0. And then we're going to subtract out all the shared electrons that it gets if it's the most electronegative, which is also 0. And so this is going to give us a 1 minus 0 plus 0, or 1 minus 0, leaving us with a 1, or positive 1. typically for oxidation numbers, you want to go ahead and include the charge. So if I was to write out the oxidation numbers for both the hydrogen and the fluorine for HF, typically what you'll do is you'll draw a line above the element and then put down its oxidation number. So I'm going to put +1 for fluorine, or sorry, hydrogen. And then for fluorine, we're going to write down -1. Alright. If we want to do another example, we can show CO2, carbon dioxide. So this one's going to be kind of similar. We've already drawn the Lewis dot structure for it once before, but we'll have carbon in the middle because it's the least electronegative of the two between oxygen and carbon. We can draw in our remaining dots. We did find out that we had to put in multiple bonds or a double bond between the carbon and oxygen to have everything obey the octet rule. Now what we're going to do is we can, since we already said that oxygen is the most electronegative element within that species, we're going to give all the shared electrons to the oxygens. So we're just saying, all right, well, let's assume those bonds aren't covalent. Electrons will reside with the oxygen. And now we can determine the oxidation numbers. So let's go ahead and do it for oxygen. So for oxygen, we're going to have our number of valence electrons. Oxygen is right here, so we're going to count 1, 2, 3, 4, 5, 6. So we get 6 valence electrons for oxygen. Then we're going to subtract out all the other electrons around it. All right, so this is going to be the unshared electrons, where we have, I'm going to just be looking at the left oxygen here. So we're going to have 4 unshared electrons. And then the shared electrons, so we have 2 bonds, 2 electrons each. So that's for a total of 4 shared electrons between that oxygen and the carbon. Then we can do our math. We do 6 minus 4 plus 4, or 6 minus 8. And that's going to leave us with a -2. Now we can do the exact same thing for this other oxygen, and we'll get the exact same number. I'll tell you guys how to deal with that in a little bit, but just realize that the math is the exact same. Then we can do it for carbon. Now for carbon's right here on the second row. I'm going to say 1, 2, 3, 4. So it has 4 valence electrons. Just counting over from the left side of the periodic table on the row it is on. So we're going to have 4 valence electrons minus all the electrons that are given to the carbon. In this case, we have 0 dots, so 0 unpaired electrons, and it's the least electronegative element in this molecule, so it's not going to get any of these shared electrons, so it's going to have 0 shared electrons for it. And so this gives us 4 minus 0 plus 0, or 4 minus 0, and so this is going to give us a +4. So when we go to do the oxidation number assignments, for the oxidation numbers, it is always the average of all those, of that given element. So in this case, this oxygen is going to be a -2, and this oxygen is also going to be a -2. So if we take the average of that, we end up with -2. So when we write out the oxidation number for oxygen in the CO2, we're going to just write down -2. When we go do it for the carbon, it's simply going to just be that +4. Now we'll go through this a little bit more in a following video, but do note that the charge for CO2 and for fluorine, there's nothing written there. So whenever the charge is not written, it's assumed to be neutral or 0. And the sum of your oxidation numbers for a given number of atoms needs to be equal to the charge. So in this case, 0 for both. So we have our positive 1 on our fluorine, or sorry, negative 1 on our fluorine, positive 1 on our hydrogen. We can add those together, and that equals 0. For the CO2, it's a little bit different. For the oxygens, we have negative 2, but we have 2 oxygens. So we're going to have to do, let's do a different color here. We're going to have our negative 2 for our oxidation number multiplied by 2 because we have 2 oxygens. Add that to our carbon, which has a positive 4 oxidation number. We have 1 carbon, and then we're going to add those together. And when we add those together, we end up getting our charge, which is 0. So all that checks out. So we did it correctly. I'll go through a little bit more on how to do this a little bit faster, but this is the basic premise behind oxidation numbers, and so you can always feel free to draw out the Lewis-Dot structures and assign things appropriately. Thank you, and look forward to seeing you on the next video.